Hi, this is Professor Jen-Mei at Cal State Long Beach. In this slide, I'm going to illustrate to you two examples of integration using u-substitution technique. In the first example, we look for the inside function to let u equal to. In this case, the inside function is the exponent of the function 5x cubed minus 7. If we do that, then the derivative of 5x cubed minus 7 is du, which then is equal to 15x squared. Don't forget to add the dx at the end. Once you have this step, you go back to the original integral to look for what you can replace out. And you see that x squared dx is the term that you need to replace out. So you go back to your du expression and look for the x squared dx. If we solve for x squared dx from there, you get du divided by 15. Now that we figured out what to replace, you go back to the original equation. Now the area where you get x squared dx, we're going to replace it by du over 15. Everything else stays the same. The 5 is there, the integral is still there, the exponent becomes u. So the original integral now becomes the integral of 5 du over 15 times e to the u. Clean that up a little bit, we get 1/3 integral of e to the u du. At this point, we already know how to integrate this simple function because the integral of e to the u du is simply just the function itself, e to the u. So we get 1/3 e to the u. And remember that once you have done with the integration process, you can no longer use the integral, and then you no longer need the differential du there. And to complete this problem, all you need to do is go back and replace using the definition of u. Remember, the problem was originally written in x. You have to go back and use x to solve. So replace the u by 5x cubed minus 7 and write your final answer, and don't forget the plus c at the end. For the second part of this problem, the strategy is to look for an expression that has a higher power. So in this case, the x to the 6th plus 12x to the 5th has a higher degree power than the term before, which is the x to the 5th. So that tells you that if you let u be equal to that term, then a differentiation process brings the degree down 1, which don't coincide with the term in front of it. So that's what we'll do. Let u be x to the 6th plus 12x cubed. Sorry, x to the 5th. Then the derivative of that, term by term, gives us 6x to the 5th plus 60, which just comes from the 12 times the 5, times x to the 4th power. And remember, it's the whole thing that's multiplied by the differential dx. Now here you pause for a second, you see you go back to the original integral, and you see what you can replace out. So notice that what's needed to go away is the x to the 5th plus 10x to the 4th times dx. And then you go back to your new expression. Are they exactly the same? The answer is no. However, you can do a simplification by simply factoring out a 6 in a du to get to a term that's exactly matching what we needed to replace out in the integral. That's x to the 5th plus 10x to the 4th times dx. So this tells us that this substitution is a good one. And so for x to the 5th plus 10x to the 4th times dx, that's all now equal to du divided by 6. We go back now to the original integral, and 2 and integral stays the same, but what's circled in blue now becomes du over 6. And what's not circled is exactly our u term, but remember that it's raised to the 3rd power. If you clean this up a little bit, 2 times 1/6 gives you 1/3, and you have the integral of u to the 3 du, and that is something that we know how to integrate easily. So we're going to do that by raising it to a power of 4 and divided by this new power of 4. Combining the 3rd and the 4th, you get 1/12, and u to the 4th. Remember to go back and replace by the definition of u to finish the problem. That's it for integration by substitution.